Go ahead.
All right, we are Team 1. We are working on the crushing element for the second design. All right, next slide.
Did that go backward?
All right, so our beta design, our initial alpha prototype, we had just a wheel. We added teeth and we've welded everything on, and we are getting ready to test it to be actually start crushing rock to see how it will hold up. Right now, we have not fully figured out our integration for our other subsystems yet with our beta prototype.
He's looking at the desktop now.
So you can't see. All right, next slide. So our key design variables, we're worried about where the force is going to be applied to the teeth, material of it to compromise price versus weight, versus how big of a crusher that we wanted. We initially were wanting a 18-inch wide wheel with a 4-inch diameter, and that we've already compromised down to 12 inches to try to save weight and cost. Our initial wheel, we were estimating it was like $400 for just the wheel, so we already cut it down in size. We wanted to know how much force is applied to the teeth to reinforce them for how much we need to hold up the teeth, or to reinforce the teeth so they don't wear out and need to be replaced all the time. And we also were considering our input torque to the shaft. So we did a hammer drop test on a rock using a 4-pound sledgehammer. We found that the rock was able to, we were splitting white marble chips, and we were able to split it at a drop height of 6 inches easily. We could get less than that, but we decided to conservatively stay at 6 inches for our force calculations, so that way we would have more force than needed to make sure that anything we designed would have longevity. We used the momentum equation to figure out how much energy impact that was and approximately how much force that was generating. So we figured out a number that was right around 250 newtons of force to split the rock. We also looked at a few other items on Google and made some educated guesses about exactly where the force would be being applied to the teeth for our FEA analysis.
So for FEA analysis, it's a little hard to see, but there's in each tooth there's a 3/4 inch by 3/4 inch section. There's 8 of those sections across these teeth, and I put a 200 Newton force on each of those sections. There's 2 teeth total with those forces on it, so there's about 3,200 newtons total in force. The displacement turned out to be like a 100th of a millimeter, so very little displacement. Also, the factor of safety was 125. That was the lowest factor of safety across the entire model. This, you can see it better. This is each section of force being applied. So overall, it handled it well. We don't expect that there will be much deformation. Obviously, over time, there would be. However, with the way we've designed this, the teeth will be taking the brunt of this force, therefore allowing us to replace teeth when necessary. Also, the entire model itself contains a hopper with a plate, a wear plate, so that the force being applied on the teeth and the force being applied on the wear plate are what we'll be considering, and the wear plate will also be something that's replaceable. We didn't run FEA analysis on that as it was not really our main concern. Since it is just a solid plate, I didn't feel as though that's our weakness.
So this is our failure modes and error analysis that we did, and by far our highest risk priority number was on the teeth, because they're most likely to wear and fatigue after a lot of crushing. Also, if they do fail, then we will not be crushing any rocks. So we made them replaceable by using a bracket that's going to be on the outside of the wheel. So those will be replaceable teeth. As far as everything else, the hopper would be the most dangerous thing to have failed, but it is also one of the least likely to happen, and it'd be very easy to tell if it is about to happen. So for sure, the teeth was the highest risk priority number, with the drum being next, just because It's going to have a little bit of wear from the crushing as well, the force of the teeth on them. So, any questions?
Thank you. Yeah. So, yeah, good presentation. Yeah, a few questions. So, I'm just trying to visualize and think. I did see the teeth very well. So, thanks for holding up to the camera. I'm just thinking. So the rock has been crushed by the teeth are grinding it. But the way I'm envisioning it is kind of the rock being kind of pinned against something, and then there's rotating teeth, and then the rock getting crushed. I'm maybe having a hard time visualizing it. So is there going to be kind of two of those that are spinning together and that are feeding the rock, or how is it going to work?
So you can see this camera.
Maybe move to your right there. Yeah,
okay.
Great. Mm-hmm.
So if you can imagine, there's going to be a wall here, and there's going to be yeah, sure. So if this was the wall here, and there's a hopper in this area that you place all of the rocks in, then as the rocks fall down, there's another plate on top of the back of this hopper that will be like the wear plate. And so as this drum rotates, it will be pushing the rocks into the wear plate, and that will be our main crushing mechanism.
Okay, got it. Okay, that makes sense. Thank you.
Yeah.
And when it's the rocks are fed in, so is there a limit on the size?
So our drum is planning to be 12 inches wide. So our rock size input is limited to probably about 6 inches. The larger it will be, I imagine, the more difficult time it will have crushing. But I guess there's no real limit to the size of the rock besides actually placing it into the hopper.
Right. Okay. Yeah. So it's there's always going to be a trade-off, right? How customized do you want it, and how much effort do you want to put in? The people that would be using it, you could always tell them, hey, look, the limit is the maximum is 6 inches or 12 inches, and they would have to say manually, break it, and then feed in that. So yeah, I don't think that's a problem. It's just maybe in the back of your mind, think if things could be adjusted, or maybe think about a little bit larger size, that might be a potential area of improvement.
Yeah, something we have considered for the output size is that the wear plate I was mentioning, since that is replaceable, we could add different thickness wear plates to be able to adjust the output size of the rock. You put a smaller plate for a bigger rock, or a bigger plate for a smaller rock.
Right. Yeah. Okay. That makes sense, and that would be something that the customers could tell you. What is the size of the product that I need. Maybe it's if you could have it adjustable, like you said, maybe that would be best, because maybe some construction you need this size gravel, and then some you need that size. So I think having it adjustable like that, it's a good idea.
Great.
Okay.